Hello, everyone. I'm Will. Welcome to the second in the Intro to miniKanren series of Hangouts. Today, we're going to talk a little more about recursion, which we talked about last time. Last time, we also talked about other aspects of schemes, such as making decisions with conditionals, if or cond. We talked about lists and pairs, cons, car, couldr, null, question mark, stuff like that. How to define a function, anonymous function, or to give something a name with define. How to write recursive definitions, all those sorts of things. So the other thing, okay, so well, anyway, we're going to finish up talking about the basics of recursion today. And then we're going to talk about some other aspects of scheme that are important if you want to write interpreters, because the progression of this is we want to talk about things that will lead up to not just talking about miniKanren, but writing an interpreter as a miniKanren relation, which is kind of the thing that we can do that powers a lot of the most interesting examples. That's how we do program synthesis. That's how this Barlaman tool that does synthesis works and things like that. So anyway, so everything we're doing is going to work towards the relational interpreter in miniKanren. So in order to do that, we need to make sure we understand recursion and any aspect of scheme that we need for writing interpreters, and that's going to include things like pattern matching. We don't technically need pattern matching, but it makes it very convenient to write things like interpreters, and also other things like type inferencers, so forth. So we'll want to learn about pattern matching, and pattern matching actually isn't built into scheme. It's a syntactic extension. It's extending the syntax of scheme. It's actually implemented as a macro. And so scheme has a very powerful and very interesting macro system. So we might talk a little bit about scheme macros. The pattern matching also uses a feature of scheme called Quasiquotation, or backquote. And so it's a form of quotation that's a little more sophisticated than just like the quote mark that we looked at last time. So that's something we want to look at. So the combination of quasi-quotation and pattern matching is very, very powerful in scheme. Allows you to write things like parsers in a very, very easy way, or interpreters in a very straightforward way, very concise way. So we'll look at all the parts we need so that we can start writing little programs that manipulate scheme programs. And this is one area where scheme, I think, really excels, is in writing programs that manipulate other scheme programs, so metaprogramming. And there's a variety of ways to do metaprogramming in scheme, but so we're going to look at macros. That's one way. We'll also look at writing things like interpreters and other programs that manipulate scheme programs, maybe generate scheme programs, stuff like that. So that's the basic outline. So we have some topics we need to discuss. But first, I want to talk a little more about recursion. And last time we talked about this approach, which is sort of a wishful thinking approach to recursion, where we when we get stuck in the recursive case, or one of the recursive cases, we pretend as if instead of writing our own recursive function, we have a library call that we can make to an existing piece of tested correct code. Someone else, maybe more experienced, or someone who's taken a lot of time to really test that code or prove it correct or whatever, has written. And so we know that that code is correct. So we are going to write our definition with respect to that code, and then make a call to that code and see how the behavior of our code, assuming we made the call to the correct definition, differs from what we expect from the example. And then we'll modify the call somehow, the recursion, maybe con something on to the result of the recursion, for example, if we're dealing with lists. And at that point, we pretend that we can stop pretending that we're calling someone else's library function and just say, oh, we're calling our own recursive function the entire time. So that was this make-believe game we played at the end of the last Hangout. So maybe we'll just look at one of those examples or two of those examples, and then I'll show you another technique for writing recursive definitions. I think is quite nice and quite powerful for recurring over nested lists, which are trees. Very powerful approach, because trees come up all the time in computer science. in many, many forms. So abstract syntax trees for programs, if you're writing a compiler or an interpreter or something like that. You know, HTML and something like that. That's a tree. And so you'll see these languages. XML is a tree. In fact, the precursor to XML, XML is extensible markup language. The precursor to XML is something called DSL, DSSSL, Dynamic Style Sheet and Semantics Language or something like that. That was pretty old. But anyway, DSL actually had a special language for manipulating, you know, DSL documents, and that language was a subset of Scheme. It was basically a subset of R4RS Scheme, an older version of Scheme. So, you know, if you're going to manipulate trees, process trees, take a tree, do something with it, and generate a new tree, you know, induction or recursion is the way to do it, because trees are inductively defined data structures, and the way you operate on the inductively defined data structures naturally is through recursion. So anytime you see tree, you should think recursion. Recursion's your friend. It's not something to be afraid of. So yeah, so we're going to look at a very nice way to take a recursive definition that works over flat lists and then modify that to work on trees. So it's a really neat trick. So that's what we're going to start with, and then we'll go into the things that we need to know in order to do pattern matching and stuff like that. And then we can start talking about shadowing of variables, free and bound variables, environments, and all those things, so we can start writing interpreters. All right, so let me go ahead and start screen sharing here. Bring up my Emacs. Let's see. I will cleverly call this foo.scm. Remember, SCM is one of the extensions for Scheme. Okay, so let's just kind of recap. You know, last time we did things like define append. Right? So append is something that's going to concatenate two lists. So we could have two lists, L and S, and we have to make a choice here. So the choice was, is L the empty list? If so, return S, the other list. Else, we're going to make a recursive call to append on the cdr of L. The reason it's the cdr of L, which is the shorter version of L, the rest of L, is that we ask the question about L, is it null? So we have to make L eventually the empty list, otherwise we'll get into an infinite loop. So we have to make sure in the recursion L gets smaller. We didn't ask a question about S, so S can remain as it is. And if you recall, the game we played was something like, you know, this isn't our append, we're calling Dan's append. And when we started out, we assumed we had some test cases like ABC to DE is supposed to generate the list A, B, C, D, E. And this allowed us to play computer. So when it came to the recursive case, we were pretending that we were calling Dan's version of append, which we know is correct. So what we did was we played computer. We took this example, and we said, OK, for this example, L, when we call append for this example, L is going to be the list ABC, and S is going to be the list DE. And that means when we ask if L is null, well, L is the list ABC, so it's not empty. So we keep going. That means we hit the else case. And now we're going to make a call to Dan's append. And the assumption we're making, this is the make-believe part, is that Dan's append is a correct definition of append. Concatenate the list that is given correctly. So what list is it given? It's given the cdr of L, which is the list BC. It's the rest of that list. So maybe look at it this way. Footer of L equals BC, and then S doesn't change, so that's going to be DE. So we're concatenating those two lists, BC to DE, and of course, what that would produce in this case would be, my indentation's getting messed up because of this. What we would get back in that case would be the list B, C, D, E. But we know from our example, we actually expect A, B, C, D, E, and we're only getting B, C, D, E back from Danzapen. So therefore, we're missing something. We forgot. And where did A come from? Well, A was the car, or the first element of the first list, L. So what that means is we have to cons on the car of L to what we get back from the recursion. And in that case, we would get the correct answer. Now that we actually have a complete definition, now is when we can pretend that, or stop pretending, actually. We can say, okay, we're not actually using Dan's append anymore. We can just use our own append. And at that point, it should all work. And let's just try this example. Okay. This. And now, try a simple. And sure enough, it works. Okay, so the important part was this make-believe that we called Dan's append, and then we thought about how that wasn't right. So how we'd have to change the answer we got back from Dan's append. The other things we pointed out last time is that when you're recurring on lists, you're probably going to ask for one of the base cases or the base case if the list is empty. And therefore, you're going to have to, in the recursion, pass in the cdr of that list if you're asking if it's empty, that kind of thing. Sometimes you want two or more lists to end up empty at the end. In that case, you might want to take cdr of both, that kind of thing. So that's the sort of make-believe that we looked at last time. So let's together, I'm going to restart scheme since I redefined append. Let's together define a little recursive relation on lists. So what would be a fun example? Any suggestions of what sort of list function we might define? Let me think. How about, well, let's see. I think we did length and, oh, okay. I know a good one. I don't think we did map, did we? Did we do map last time? Oh, okay. We got a couple suggestions. Filter and rember. Those are both good ones. All right. So let me write it down. So we got filter, we have rember, and let's say map. Okay. So I don't remember if we did map last time. Okay. So let's try knocking those out real quick. Just give us a little practice. All right. So filter, you can actually define it one of two ways. You can do a filter in or a filter out. Actually, of the three, I think probably the easiest of these, or the simplest of these, is rember. So let's start with that. Okay, so rember is going to remove the member, or remove an element of a list. And did we do member last time? I don't remember if we did member. No. Okay. Well, so let's just practice our recursion a little bit. So let's do member and then rember and then filter and then map. And we should be able to do these pretty quickly. Just go through the steps. Okay. So member takes let's say a symbol, a quoted symbol, and it takes, let's say, a list of symbols. And what it's going to return is true if that quoted symbol appears within the list of symbols, and it's going to return false if the symbol does not, like that. And it doesn't matter if the symbol appears more than once. As soon as you see it once, that's sufficient, okay? And when writing recursive definitions, if you're recurring over lists, usually you want to try to figure out what does the empty list do? Because usually that's going to be your base case. So, is the symbol X a member of the empty list? Well, clearly not. Okay, so now we have some examples, and that should help us figure out. If we want another example, maybe we can have another example where X is the beginning of the list. It doesn't really matter. All right, so now we have a bunch of examples for member, and we can go ahead and define it. So let's work through the process. So if we're defining a function, we know we have to write define. We haven't had to think any so far. What's the name of the function? Well, from our examples, we know it's called member. Haven't had to think. We're defining a function, so we have to write lambda. Haven't had to think. Lambda, okay, we have to decide how many arguments it's going to take. Well, all of our examples have 2 arguments. We have some symbol, and then we have a list of symbols. So now we have to maybe think a tiny bit. We have to decide what we're going to call the identifiers. And by convention, I'm just going to call something like a symbol X. Sort of, the fact that I called them X here is sort of coincidence. I could have another example where I call them something else like foo. True. And then I have a list of symbols. So I could call that L for list, LS for list. I could call it LOS for list of symbols if I want to sort of give it a name that reflects the type. I'll just call it L. So we have some symbol and then some list of symbols. And I had to think a tiny bit about that, but if you have conventions for these things, you don't really have to think much. We know we're going to have to make some decisions, so we have a con. We are going to have a con. We're going to have at least 2 clauses because we know there's a recursive definition. And why the reason we know it's recursive is that we have lists of various links, and the only way to deal with that in a reasonable way is with recursion. So we know we have at least 2 cases. We know that else is going to be the clause for one of them, or the test for one of them, the last one. And furthermore, because we're recurring on lists, it's almost certainly the case that the recursion should be on the list because that has structure, unlike the symbol. So we're going to be looking at L. That's what we're going to be changing in our recursion. And since it's a list, our standard test for the base case is to ask if it's null. And so far, I really haven't had to think. This is all basically automatic. What I do have to think about is how many clauses do I have? Do I have other tests here? Besides the recursion, and so do I have to make a decision if it's the empty list? Well, yes. I have to have the null test so I don't keep going past the empty list in my recursion and get an error. Because remember, we can't take the car or cooter of the empty list. So I need the null test. But there's also a decision I have to make about X itself. So I have to decide if the first element in this list happens to match X. Okay, so I have to look at X, or foo, and I have to decide if the first element of this list is the same as foo. So I do have to make a decision here. So I have another case in my con. So I know I'm going to have another case here. All right. But that looks like that's it. So I'm going to have 3 con cases. So my program's starting to take some structure. And I know that this is going to be a recursive definition. So I know at least the else case is going to have a recursion probably. So when we get to those cases, we'll do some more not thinking if possible. All right. Well, we know we have a case for the empty list. What do we return? Well, we already did our thinking up front when we came up with our test cases. We decided what should happen if we call member with the empty list. It doesn't matter what the symbol is, we're always going to return false because there's no way that symbol is a member of the empty list because the empty list doesn't contain anything. So the null test is going to return hash f. Okay. One thing I should point out is that even at this point, we could start testing member. So if we had, if we got rid of the other two clauses, this is actually a valid scheme program, this definition of member. And so we could test it on the empty list case. So we could test this version of member just on the empty list. I'll show you that. So we grab this version of member, and I can try it. Empty list test. Sure enough, it behaves correctly. Now, if I try it with any other lists, it's not going to work because we haven't added the other con clauses. But this is just a demonstration that as you're writing your recursive functions and building up the cons clause by clause, you can actually test things. And this also will happen when we write things like interpreters with our pattern matcher. We don't have to write the entire definition before we can test it if we want to. So that's, if you're working on something complicated, maybe you want to test it as you go and sort of build it up. So that's a technique that sometimes I use. Okay, so we know the null test, that's done. We know the answer just from our test case, that's fine. And now we're getting to these more complicated cases, all right? So we have to make a decision to see if the first thing in the list is equal to our first argument, x. And if so, then we're going to do something, otherwise we're going to do something else. So let's think about this. So our test is going to depend on some form of equality. Okay, so we could use something like schemes equal, question mark, or equal, huh? So we want to know if x, our first argument, is equal to the first element of L. Okay. Now, equal is symmetric. It's a predicate. It always returns true or false, and it's always going to terminate in these cases. But I'm going to swap the arguments so that the car comes first. That's just a stylistic thing Dan Friedman taught me. And the reason he likes to do it this way is it's a little subtle, but since we're in a language with a lot of parentheses and not a whole lot of syntax, there's lots of right parentheses in the expressions you write. So if I have the car of L come at the end, then notice that there are two right parentheses here. Whereas if I swap the arguments and have the x come last, there's only one right parenthesis. So Dan finds that a little easier to read or to parse visually, and I agree with that. So that's how I'm going to write it. It's a little stylistic thing. So what's going to happen if the car of L is equal to x? What should we do? And so we have some tests up here where, we can think about it. So if the car of the list is equal to the thing we're looking for, well, then definitely the symbol is part of the list. We know that's true. So we don't have to do any more work. We can just return true at that point. Let's bring it up to the last line. Okay, so in that case, we're going to return true. And so notice we don't have to do a recursion in this case. We're already done. All right, so the else case, what does the else case mean? So the else case means that the first element of the list is not the symbol we're passing in. So this case would be like if it were the first element. So the not case might be like this element. So the first thing in the list might be A, and we're looking for X. Okay, in that case, well, no, we're not finding what we're looking for. So we're going to have to look through the rest of the list to see if it's there. So that means we have to make a recursive call. Right, so we're going to have to make a recursive call to member. Okay, so we know how many arguments member takes. It takes X and it takes an L. And remember, our base case is when the empty case, or the empty list, that's our final base case. We have another case that we terminate the recursion when they're equal. But this is the case where we really have to worry about, we can't go past the null list. We can't take any coulders of the null list or we're in trouble. We'll get an error. So, so for L, that argument definitely has to get smaller. That list has to get smaller. We have to take a couldre of it. What about X? So X is just a symbol. It doesn't have any structure in it. It doesn't make sense to take like the car or the couldre or to tear apart a symbol. It's atomic. So x isn't actually going to change in the recursion. We're just going to leave it as it is. Okay. Now we do our game of make-believe. So member is actually, we're going to pretend it's not member. We're going to pretend it's Dan's member, and that this definition is correct. Okay. So let's look at a couple of our test cases. This is where you have to maybe be a little careful with your test cases as well. If you're going to play this make-believe, think about it a little bit. So here's a test case that I know will work with the make-believe. Other test cases, we might get in trouble, might mislead us. But let's try this one. So in this case, we know that x is literally the symbol x, and we know that L is a list XFG. So is the list XFG null? No, it is not. Oh, whoops, sorry. This is not the one that we want. We want, I don't like thinking about this with the make-believe. Oh, yeah, this does work. Yeah, of course, okay. I was thinking, oh yeah, well, what are we going to have to do outside the recursion? Well, the reason that it's kind of hard to define a test that doesn't work is that all the tests work because all we have to do is recur on the rest of the list. There's nothing we have to do on the outside. So if we try all these tests with the make-believe method, they should all pass because all we have to do is make a recursive call to number. There's nothing we have to do outside of that. Now that's kind of funny. I hadn't really thought about that before, but you know, if all you have to do is make a recursive call, there's nothing else to be done. And you can still do the make-believe method, but you'll have trouble finding any arguments that don't work. All right, and then I think we're done. So let's just try this. Try this definition. Let's see if I'm lying about this. Right, let's try our cases here. False, that's right. This should be true. This should be true. This should be false. This should be true. This should be true. Okay. So that one's kind of interesting because we don't have to do anything outside the recursion. It just works. Great. So that's member. Okay, so let's do rember. Rember is kind of the next step up. And so rember's name reminds me of member. That's why I wanted to do member first. So what rember does, remove a symbol from a list. So, you know, if we had one of our examples up top, what we're going to do with rember is remove the first occurrence of x from that list. And so in that case, we're going to get back a list with the first and only first occurrence of x removed. So in this case, we're going to get fxg. And from that, we should be able to think of a couple other cases. Well, x maybe doesn't appear in the list at all. Fg. In that case, we just leave it as fg. Or we might do rember of the empty list. So it's just going to be, because it doesn't, there's no way x can occur in there. So that's what rember looks like. That's remove a member of the list if it exists. And we're only removing the first occurrence. That's important. All right. So we do the same thing. We know it's called rember. We know we're defining a function. We know it takes 2 arguments. Call it lns. Do a cond. Okay, and so at this point, it should be becoming second nature. We know we're recurring on the list, so we're going to have a null test. We actually have our case for null already, so we can just go ahead and write that as we're writing our definition. We might have to make a test here, and we probably have an else there. Okay, So we're going to have to make a test to see if X is the first thing in the list. This is exactly just like member. So we can literally just copy this test. So we want to see if the first thing in the car of the list is this X that we're looking for. If so, then we're going to do something. Okay, else we're going to do something. All right. So that's the basic structure of Rember. And basically, we haven't had to think any to get this level of structure. It's pretty much automatic. In fact, since we know it's a recursion, we already know that we're going to call Rember, and we're going to call it on X, coder of L. So that part we know already. We don't know if anything's going to come outside the Rember. So that's already basically automatic. So we have most of the program written in this case already. That's the beauty of writing recursive definitions over lists in this style, is that they almost write themselves, and there's sort of methodology to it, a bunch of rules of thumb and so forth. And once you've done a bunch of these, they sort of become second nature. Okay, so now we can ask what's going to happen in this case where the thing we're looking for occurs first. So we're seeing if X appears in this list, and in this case it does, is the first thing in the list. And so what do we return? fxg. So what is that? That's just the coder of the list. We're just returning the rest of the list. The coder of the list. We don't have to recur in this case. Because remember, we're not removing every occurrence of X from the list. We're just removing the first occurrence from the list. All right. And now we get to a recursive case, and this is when we get to do our make-believe. So we're saying this is Dan's Rember. All right. So if it's Dan's Rember and it doesn't occur the first thing, I can add one more case, so just to sort of exercise the different possibilities. Like that. So let's play computer here for a minute. We can walk through a couple examples, but let's do this example. And so in this example, L is going to be fxg. X is the symbol X. So we're going to call the recursive call on the symbol X and the list fxg. And if this works correctly, then we should just get back fg. We can also do the similar example with this case, and we'll just get back fg itself. So, like, we don't have to do anything. We're done in this case. All right, great. So let's try our Rember. See if this works. And a lot of these examples, by the way, are programs that you would see in the Little Schemer, which is really not a book on scheme. It's a book on thinking recursively. So that's a book Dan wrote with Matthias Fleisen. Oh, okay, so I did something wrong here. Oh. Okay, what did I do wrong? Oh, yeah. I didn't play the game right, did I? Oh, yeah. I totally messed up the game. All right, so what did I do wrong? Someone help me out. I got a little too eager here. Not consing, yeah. So, so if we're playing, that game, let's say this example again. Okay, this example. Then in my recursive call, I was playing make-believe a little too much. So that's what we're passing in, the fg. Oh, okay, now I know why I did it wrong, because I forgot to take the coder. So that is, fgx is indeed L, but I forgot to take the coder of it. So that's the coder is xg. And in that case, if Dan's recursion works correctly, this is Dan's Rember, then it will remove the x and we'll get back g. Okay, so that's right. But remember, we want fg back, not just g. So, so yeah, I forgot to take the coder, so I have to do that. That's important to do. So that means that we're missing the f, which is the first thing. So what we should be doing is consing the car of L onto the recursion. And then at that point, it's safe to turn it into rember. Yeah, so I was getting a little ahead of myself because I forgot to take the coder when I was making the call to the library function that we think we have access to. So let me find it, and let's try these examples again. Empty list shouldn't have changed, and the first case is fine. The second case, okay. All right. So now we're okay. So yes, that's the important part. Was like we have to remember if we're going to use the this methodology, we have to remember to take our coders and so forth when we're playing make-believe. All right, so that's rember. Let's do a slightly different version of rember called rember star. And rember star is just like rember, except that it removes all of the occurrences of the symbol from the list. So here we had 2 x's, so both x's get removed. Otherwise, it's the same. It's no different. Okay, so this is rember star. And if we wanted to, we could kind of modify rember to be rember star. Just start off by changing all the recursions. We could build it up from scratch if we wanted to as well. You know, if we're doing it right, we could probably get rid of the right-hand sides. That's kind of where the action is. Everything else is going to be the same. So let's just build up the right-hand sides again. So we have the null test. We can just look at our example. So that's going to be the empty list again. Okay. We have the equal test, where we have the carve, L, and X. So let's look at one of those examples. So here's a case where the symbol we look for is the first thing in the list. Except now we can't just take the coder of the list. The coder of the list would be fxg, but we want to get back fg. So that doesn't work anymore. We can't just take the coder. So what we're going to have to do is a recursion. We know we're going to have to make a recursive call to rember star. And in the else case, we're going to have to make a recursive call to rember star. Okay, so let's think about our arguments. So x is atomic. It doesn't change. We're taking the coder of L because we have to get closer to our base case. So in both cases, we're going to have the same recursive call. And now we have to decide if something has to happen outside of it. Okay, so this is when we can play the game with the ends rember star. We have to make sure to take our coders this time. All right, so let's take this example. So the coder of that list is going to be, so here's the actual list coming in. So let's remove the first element. That's the coder. And x is still x. So let's pretend that we're calling the correct definition. The ends rember star, which is written correctly. So remember, rember star should remove all of the occurrences of that symbol from the list. So from Dan's rember star, we will get back fg. Okay, we'll remove the x's. And fg is what we're supposed to get back for the entire call. So we're actually okay with that recursion. We don't have to do anything on the outside. So just make that a recursive call. All right. Else means that we didn't have the first occurrence. The first thing in the list is not the symbol we're looking for. So that'd be like this test. So let's grab that list. Let's do the same sort of thing. So in recursion, x is still x. L is fxg. So we have to take the coder of L, which was the mistake I made before. So we have the list xg. And if we make the recursive call in Dan's rember of x and xg, well, we remove all the x's from that list, so we'll just get back g. But if you notice, we're supposed to get back fg, not just g. So once again, we have to make sure to cons on the car. This is exactly the same as in the definition of remember above. We have to do that, add the cons. And now we can get rid of the Dan's remember star and just make it remember star. So let's try that. Okay, so those all seem to work. Now I see a comment in chat, not consing. Okay, I'm not sure if I understand that. Did I make a mistake, or is that okay? Oh, that's hold. Okay. Oh, I see. Okay, that was because before I messed it. Gotcha. All right. So so we've got remember. We got remember star, which allows us to recur of all the elements of the list. And I'll show you one other variant of remember. And this is something I talked briefly about at the end of our hangout last time, but it wasn't recorded. And let's do one more version of remember. And I will call this deep remember, or deep remember star, or I don't know what to call it, maybe deep remember star. The deep remember star is going to be like remember, but we are going to have some additional fun here in that it's now the list that's passed in can be a nested list. So this list can now contain multiple elements. So we can have things like, actually make this like checks. You know, so we can make something quite complicated where we have lots of deeply nested structure. Making up something like that, okay? And what we want to do is we want to remove the x's from everywhere in the list, everywhere they appear. And so our remember star doesn't really work that way. So let me show you what happens with our current remember star if we gave it that list. So in this case, I don't think it removes any of the x's because none of those x's appear at the top level of the list. I can give it, actually what I should do is modify this list to give it an x at the top level also. Maybe I'll give a couple x's at the top level. Okay. All right, so now we'll remove some x's. But you'll see that the x's that get removed are only the x's at the top level. So we had this gx here, so that x gets removed, and then we had an x at the end with the xb, so that x gets removed. But most of the x's, any of the x's that are nested, okay, so this definition only works for what we might call a shallow list, where we're only looking for the x's at the top level of the list. So we want to do something a little more sophisticated, where we actually remove the x's no matter where they occur in a deeply nested list. So in this case, let me make sure I get my input. Input. Okay, in this case, what we want to do is remove all of the x's in the list. So those x's go away, and this x goes 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 away. So we want something like that instead. Okay, so this is a deep, what we call a deep recursion. We're going to recur all the way down the tree. And of course, some of the other tests are going to be similar. In particular, the other simple test is the empty list, and that's going to be the empty list. So the question is, can we write a definition that works on this deeply nested structure, or this tree-like structure, without having to completely redefine a remember star? So let's give this a try. And let's try this approach where we're just going to rename it deep rember star. So we have to change all of our recursive calls to match the new names. That's the same. And what we're going to try is adding one new clause right after the null. So here's our new clause for deep recursion. It comes after the null test. And what we're going to ask is if the first thing in the list L, which can now be a deeply nested list, is itself a pair. So is the first element of L a pair? So we have to put this clause after the null test because we're not allowed to take the car of a list if it's empty. So that's why the null test has to come first. But we can ask, is the first element of the list a pair? And if so, what we want to do is do a recursion on the quitter just like we did before. I can just lift that up. But we also want to do a recursion on the car of the list. So we're going to recur on both the car and the quitter, and then we're going to try to put those back together. So because these are lists, let's see if we can put them together back with cons again. So I'm going to cons the recursion on the car of the list with the recursion on the quitter of the list. And let's see if this works. You got it right. For the base case, that surely should work. Sure. Let me try the other case. We should get that. And sure enough, we actually got the answer that we expected. Okay. So what was really interesting to me is that we had a program that we were able to write using our normal rules and our normal reasoning that worked on just flat lists, and we were able to modify it to work on deep or nested lists or trees without modifying any of the existing code. All we did was add a new clause, and the new clause had a certain structure. We asked if the first thing in the list is a pair, and if so, we're going to recur on both the first part of the list and the rest of the list, the car and the quitter, and then combine those recursive calls, the results of those recursive calls. And because we're dealing with lists, we're going to combine them with cons. Every once in a while, you would combine them with append, but usually with cons. If we were recurring over a list of numbers, and this was something like sum or summing up numbers, then instead of cons, because we're getting numbers back, we would use plus to add those numbers up. So anyway, this I think is a really beautiful technique. So this is something that I learned from Dan Friedman's class, and I thought this was really amazing. And whenever Dan presents this, he wiggles his fingers and he says, "Watch closely. At no point in time will my fingers leave my hand," because he thinks this is really magical, and I think it's magical too. So I really love this, that we can write a definition for flat recursion, and then without modifying any of our code, just add one new clause, and now it works on trees. I think it's so beautiful. Allows us to test our code as we're going along and so forth. So anyway, that is deep rember star, and it's an example of recursion over trees or deeply nested lists. Okay, so for a rember, we also did rember star, and we did deep rember star. All right, so in order, and just kind of, we could obviously do this all day. Let's just do filter, which is the other suggestion we got. And filter is interesting because that's a higher order function. It's a function that takes a function. Map is also a higher order function. So they're sort of similar in nature. Map is pretty easy to understand. So maybe just like give an example of that. If we want to do something like map a function over a list, so maybe we'll have a function defined with Lambda that takes a number in and then multiplies in by itself. It just squares that number. And then we can multiply that we can map that over a list of integers. And what will happen is map will create a new list with the same length where it applies this function to each element of the list. So we're going to square 1, 2, 3, 4, 5, and 6. And when we get back a list, sure enough, we get a new list which has a square of each of those numbers. Okay? So map is a higher order function. It takes a function and applies it to the elements of the list. Filter is also going to be a higher order function. It's going to take a function and it's going to apply it to elements of the list. So let's see. I forget the default in Scheme because you can either filter in or filter out. So let's try something here. I don't remember which one this is going to do. But we're going to apply the built-in Scheme predicate odd, which returns hash t or true if the number is odd, and otherwise returns hash f or false. So we're going to apply the odd test to each of the numbers, and we get back 1, 3, 5. Okay, so this is filter in. So what that means is that any element in the list for which odd returns true, that's what we're going to keep in the new list that we build up. Otherwise, we're going to throw away that element and ignore it. Okay, so we're just going to apply this function to each element. So we can either use some function that's already defined or that we've given a name to, or we could define it using we could define our own anonymous function, or sorry, not define it, just create an anonymous function. So here's an in, and I can say, I don't know, if I take in minus 1, this is a stupid example, but is that even, right? So this is basically just defining odd, and then we get the same example, or the same result back. Okay, so I can define my own anonymous functions as whatever. So this is what filter does. It takes a predicate and then it takes a list. So let's create a couple of examples here. This is filter in. Remind us. And of course, we have an example where we have the empty list, and we're just going to get back the empty list. In this case, we're going to get back list of odd numbers. Okay, so that's probably enough of an example. Let's work through it again. Find filter, we know that much. It's going to have a lambda. We know it's going to take 2 arguments. Now we have to think a little bit what argument are we going to give. We could give p for predicate or f for function. I tend to give f for function. And then we have a list. Okay, so I didn't think about it too much. I know it takes 2 arguments. I give them some names according to my conventions, which are fairly standard. And I know I'm going to have at least 2 con clauses. I'm going to have at least an else. This is a recursive definition, so I know I'm going to have what's called a filter. F is an atomic value. You can't tear apart functions. So F is going to be passed along, but I need to get closer to what's going to be my base case, because obviously I'm dealing with lists, so I'm going to have a base case of null. I may have another case here. All right, so already I'm starting to fill out the structure and not really having to think. Okay, this is the important thing, is to not have to think, and this should become automatic. So what do I do in the null test? I don't have to think there because I've already written my test. So I just grab the empty list. I haven't had to think yet. All right. I might have to do something outside this called a filter. I don't know about that yet. So I'll have to think a little bit there. And then let's see if there's another test. Well, do I have to make any decisions based on the elements of the list? I do. I have to decide whether or not a number is odd or not. Right? In order to decide whether or not the elements should be kept. So I'm going to have to make a decision here. So sure enough, I'm going to have an extra clause. Okay, so what's the decision I'm going to have to make? Well, I'm going to have to make a decision based on the car of the list. Usually when you're making a decision on the list, you have to make a decision based on the first element of the list, because that's what you have access to as you're cutting down. And what do I want to know? I want to know if this element is odd or not. Okay, well, how do I know it's the odd test? Well, it's because it's whatever function has been passed in. That's the function I'm going to apply to that element. So what I have to do is a procedure call. I write with the parens. So here I'm applying the function f, which was passed in, to the car of the list. All right, so that's my test. Might look a little strange if you're coming from a language like Java or whatever, the syntactically, but this is a function call. Remember, the parentheses in scheme always mean something. So that extra set of parentheses means that we're calling the function f, and its argument is going to be the car of the list. So if f is odd question mark and the car of the list is 1, then we're calling odd question mark on 1. Okay, so what should we return? Well, let's think about this. So if we were playing a computer and f happened to be odd, so f is odd, and the car of L happens to be 1, so odd of 1 happens to be true. Okay, so if that's the case, then we want to return 135. Well, look, we have to do a whole bunch of stuff with the rest of the list, and we're not just returning the footer of the list. So that means we're going to have to make a recursive call. So here we have a recursive call. Same reasoning as before. F is atomic, so we leave the F there. We're going to have to get closer to the base case with the curve. So we know that much. And now we can play our standard game. This is Dan's filter. All right. So assuming we call Dan's filter, and Dan's filter is written correctly, so F is going to be our current, our current F, which is odd. And the footer of the list, so here's our list, and we have to remember to take the footer, like I forgot last time. Okay, so the footer of that list is going to be 2, 3, 4, 5, 6. And remember that Dan's definition of filter is always correct. So this is going to just keep the odd elements. So that means we have 3 and 5 in that list. Great. And if you look at what we expect to get back, we expect to get back 135. What is 1? That's the car of the list. It's the first thing there. So I'd better cons on the car of the list, which is the thing I made a test on now. I applied F to the car of the list, and if that returns true, then I want to keep that element. Okay, so at this point, I can get rid of Dan's filter and replace it with a little cursor called a filter, and that should be correct. All right, now we have another recursive call. So let's look at that. Play the same make-believe game. So this is Dan's filter. We know from the last example that F is going to be odd. Footer of L, flip that around, I guess. That's going to be same list. So we have to remember to take the footer. Okay. And so if this is Dan's filter and it works correctly, once again, we will get back 35. Okay, is that the correct definition? Well, we need another test here where the first element in the list isn't odd, so something like that. In this case, we should get back 35. Okay, so in this case, we actually are getting back the correct definition. So notice what I had to do is I had to add another test so I can exercise each of the clauses, the base case and each of the recursions. So if I didn't have a test that exercised this recursive case, I need to add one. 5 is exactly what we expect. Not to cons anything on the recursion. Basically, we're trying to forget the first element in this case. If the function we pass in returns false, we want to forget that element and just not cons it on. So that's how we forget or remove an element. We're not really removing the list. We're not destructively removing it. We're just forgetting it when we build up a new list. We just forget to put it in. Okay, so if you're new to functional programming, this is one of the differences between functional programming and imperative programming. We're not modifying the old list, the list L that got passed in. We're not changing it. We're just constructing a new list. And that new list just isn't going to contain all the elements necessarily of our old list. And that's how we remove an element from a list. Removing an element from a list is not really what we do. It's just kind of shorthand for saying what we actually do, which is build up a new list that just doesn't contain that element. Okay, so we're not really removing anything. The old list is still there. So let's try our filter. 3 cases. Base case works fine. The odd case, fine. Another case works fine as well. Okay. And let me just prove to you that we're not modifying the list. So if I say define my list to be, say, this list. My list is that list. And now I can call filter of odd with my list. I get back the expected list, but my list does not change. So we have not actually modified my list at all. So this is one of the ideas of functional programming. We're not going to change the values of data structures like lists. Instead, we're going to build up new lists. And this allows us to access the old list, which we might want to do for various reasons. One reason is, say we're running on a parallel computer, or a computer that has multiple processors or multiple cores. We want to do some parallelism. Very difficult to reason about a program if different parts of the different parallel threads or of the program, of the execution, are modifying the same data structure. Now you have to start worrying about which thread is accessing the data structure. Do you have to lock the data structure? All these sorts of headaches. It's very, very tricky to get right. And so instead, we're just like, no, let's create a new list. And the old list is going to be the same. It allows all sorts of sharing of data structures and so forth. So that's one of the fundamental ideas of functional programming. So we're not going to modify the data structures. Instead, we're just going to construct new data structures. Okay. So those are a few definitions, and I won't bother to define map. If you want to try map, you can try it on your own. I think filter is interesting because it's higher order. We're passing in a predicate. And this sequence of rember star, deep rember star is interesting because you can see that we're growing in sophistication and our recursions are changing. And in particular, the deep rember star is interesting because we use this new trick of taking a function that's defined over flat lists and then modifying it by not changing any of the code, but just adding one new clause in the coder, and we have this special test to see if the pair of the list, of the car of the list is a pair. And so we have this new pattern that comes up over and over again when you're taking a function that works over flat lists, and then you want to make it work over trees or deeply nested lists. So I think that's pretty interesting. Okay, so that's pretty good, I think, intro to the sort of basic ideas of recursion. Obviously, we could spend a lot more time talking about recursion. It's a very interesting, deep topic, but I think that's certainly enough to get us started. Recursion over lists is kind of bread and butter for list programming, and I think that should serve us well. About that before we go on. How did people like that trick of the deep recursion? Had you seen that before? Don't be shy. So last week I was talking, yeah. Anyway, so that's there are other ways to write recursions over trees. So that's not the standard way to do it. There are other ways to do it, but I think that's and we'll see some other ways when we write recursions over Lisp functions or Lambda calculus and stuff like that. We'll see another way of doing the deep recursion. But anyway, I thought that was really neat that you could do it without changing any of the existing code. I thought that was really neat. Yeah, and I've been programming a long time before I saw that trick. Okay, so we've got a pretty good handle on recursion now, at least recursion over lists. And now we want to try to think about what's the next thing we need in order to make progress towards our interpreter. So there are a couple of concepts we need to talk about. We need to talk about things like environments and lexical scope and variable shadowing and all that. The other thing we're going to need is some features of scheme or added to scheme. In particular, we're going to want to use some pattern matching, and we're going to want to know about back quotes and commas. That's going to turn out to be really useful. So probably the thing to do is talk a little more about scheme. Let's talk about back quote and comma, and then we can get into some pattern matching and some macros. At that point, we'll be ready to start talking about sort of how scheme gets evaluated and the environments and all that stuff. So let's talk about quotation and scheme a little bit, which is a very interesting and very deep topic, and I'm only going to really it'll be enough to get us going. All right, so quotation. We've already seen one way to quote something in Scheme using the quote symbol, or the, I don't know, you want to call it tick or something like that. And so remember, I think we saw some examples like this. So plus v4. So if you remember, if we want to add two numbers, we can call the procedure plus, and we get 7. We evaluate that expression of the REPL. But if we put a quote mark in front of that list, then we get back the list. And so something I should tell you, if I haven't told you already, is that that quote symbol is actually a shorthand. And so this expression with the quote is equivalent if I can type to this other expression. So I'll show you. Quotes plus 3, 4. I get back the list plus 3, 4. So this is a special type of syntactic sugar that you can get in Scheme. So there are a few of these. There's that quote. There's another type of quotation. There's a comma. We'll see in a minute. But anyway, this tick mark is really, and basically when the Scheme system reads in this expression at the REPL or reads it in from a file, it's going to internally convert it to something that looks like this quote. Some Lisps have something called reader macros, where you can define special shorthand syntax like this, which will then turn into things like quote. So notice that this quote thing is a little weird because normally we're writing everything with parentheses. So sort of the fundamental underlying version of this, the internal version, if you will, is this quote form. But because we use quotation so much in Scheme, it's a little awkward to type that way. So there's this shorthand, single quote symbol. But you could write it either way, and it works the same. All right, so that's quotation. And if you wanted to think about this as a rule, the rule is if you quote some datum is a singular of data, that gives you back the datum. So anything we quote, we just get back that thing again. This is the idea. So that's the rule. So we can quote anything we want. We can quote foo, and we get back the symbol foo. We can quote some list, ABC. We get back the list, ABC, and so forth. Okay. And in fact, when we write an interpreter, we're going to add exactly that rule to the interpreter. Quote of datum gives us back datum. Mention that there are other versions of Lisp that have somewhat different semantics. There are versions of Lisp where you would actually get back the quoted form, where quote of datum would give you back not datum, but rather quote of datum, where it keeps the quotation on it. And there are some reasons you might want that semantics, but that's not the way Scheme works, and that's not the way we're going to do it. But just be aware that there's some system. In fact, I believe in Racket by default, if you do quote of foo, it'll give you back quote of foo, not foo. But in Scheme, quote of datum is datum. All right, so that's sort of this simple rule. Quotation is a very deep idea, and logicians have studied this. Philosophers have studied the idea of quotation for a long time, and there are all sorts of arguments about how quotation should work. And when we look at quines, quotation will be very important in our definition of quines. There's programs that evaluate themselves and so forth. But anyway, the simplest version of quotation we have in Scheme is this quote character, which expands into this tick or whatever, that expands into this quote form, and quote of datum is datum. By the way, quote is not a function. Okay, so remember when we were playing around before with adding 3 and 4, if I type in plus, Plus is basically a variable that happens to be bound to a procedure that knows how to do addition. Okay, so I can ask procedure question mark of plus. So any procedure I create, like with the lambda XX, that's true. If something's not a procedure, like 5, procedure question mark is going to give me false. Now, if quote were a procedure, I would be able to ask procedure question mark of quote. So let's see if it's a procedure or not. In fact, not only is it not a procedure, but I get an error from trying to make this call because quote is actually special syntax. So you can see the error I'm getting, invalid syntax quote. So quote is a special form, a special syntax, and you can't just, it's not really, a variable bound to a function like plus is. Whenever you use quote, it's expected to be used in this special way where you're quoting some datum. So if I do quote with no arguments, I get invalid syntax. If I do quote 1, 2, 3, I get invalid syntax. So the only time quote will work is I give it a single datum, and then it'll be happy. Okay. So that's an example of a macro, or I shouldn't call it a macro. That's an example of a special form. It has a different evaluation rule than the functions. And when we get into implementing scheme, we'll see that a little more clearly. By the way, there are other things like Lambda, which are also special syntactic forms. So I can't just type in Lambda. Things like cond, we've already seen cond, if. So there are a number of built-in special forms in scheme that are not procedures, and they're not bound to procedures, and you have to use them in a syntactically correct way. All right, so that's quote. Quote of datum gives you datum. And let's look at another form of quotation. There's another form of quotation called quasiquote, backquote, backtick. People call it different things. Technically, it's called quasiquote. And it has a different sort of quotation character here in the shorthand form. Let's get the backhand. So the back quote. So normally, that's the character right below your tilde. The character, sorry, like tilde. If you do shift of this character, this key, you get tilde, and if you just hit that key, you get the back quote. And we can back quote, a list. We can back quote other things. So let's start with the list. Let's say I do ABC. That is equivalent to, just like our other form of quoting is equivalent to saying, that's equivalent to quasiquote ABC. Okay. So once again, we have some shorthand form just because we type these things enough that it'd be kind of awkward to read it otherwise. So what is quote ABC or back quote of ABC? That's ABC. What is quasiquote of ABC? List ABC. So this looks, in terms of its behavior, very much like quote, because quote of ABC is ABC. And in fact, if you just use this quasiquote on the top, outside of some datum, and you don't do anything else, it's going to behave just like quote. So that's not very interesting on its own. However, there's something else called unquote, or comma. And the unquote or the comma, I can do comma X or something like that, and that is equivalent to unquote of X. Once again, we have this shorthand. And so the important thing is that I can use quasiquote and unquote together to create almost quoted data. All right, so the simplest example would be something like this. So let's say I defined X to be 5. I'm going to define X to be 5. X is 5 now. And I want to create a list, that contains some numbers, and I want it to also contain the value of x. So say I want to construct a list, 3, and then it's going to contain the value of x, and it's going to contain 17 or something, okay? So how could I do that? Well, I could call list of 3, x, and 17. So of course, x is 5, right? So this should give us back 3, 5, 17. So if I create this list using list, 3x, 17, when we look up x, we get back 5. Great. I could also construct it with cons. Like I said, cons of 3 onto cons of x, onto cons of 17 to the empty list. This is equivalent to that list call. Same thing. Great. And the reason I might want to refer to x instead of just saying 5 is that maybe in the future I want x to be 6. So if I define x to be 6, I want this same expression to now give me 6 instead of the 5. Okay, so this x thing maybe can change. So when I'm building this list, some of the data in the list is always going to be the same. The 3 and the 17 is basically constant data, but this x is not constant data. This x, I want to look up the value of the variable or evaluate it, the expression. So the idea here with the quasi-quote is building expressions. Usually you're building lists that for which most of the data is constant, but some of the data might change. Okay, so almost constant data. So here's an example where x depends on what the definition of x currently is, but the 3 and the 17 are never going to change. So the way we could define this is we could say list 3, comma x 17. So this is a shorthand to building up the list with list or cons or whatever. We can use this unquote and the quasi-quote and unquote. So this is equivalent to writing quasi-quote, unquote, x 17. Let's try these two expressions. And you'll see that they also give us the list 3, 6, 17. And you can also see probably why the back quote and the comma notation is nice, because this list looks pretty awkward to read. However, this list with the back quote and the comma is actually quite nice to read if you don't get scared by the back quote and the comma, because you can see that this list looks really, really close in structure to the list 3, 6, 17. If you look at how close those two lists are, it really is pretty nice notation, because the x we want to replace with this value 6. So that list looks very similar. It's a list of 3 elements, and the x gets replaced by its value. So this is nice syntax to read. It's much nicer to read that than to read this cons expression, which is quite complicated. And it's nicer even than reading the list expression. So when we're building up lists that contain mostly constant data, we're going to tend to use this back quote operator quite a bit. Okay, and in particular, we're going to use it with pattern matching. And the combination of pattern matching macros plus the quasi-quote syntax makes it very, very nice to do pattern matching in Scheme. So anyway, that's the idea of quasi-quote and unquote. And let me give you another example. So let's see. Have I talked about let? I don't remember if I talked about let. Let is a way to create a variable, which is going to be local in scope. And I can give a value to that variable. So just like before, I was defining at the top level a value for x. So here I'm going to make a local definition. So I'm going to say, just return x. So let x be 7. So x will be defined to be 7 within the body of the let. And in this case, we're just returning the x. So let's try evaluating that. Okay, sure enough, I get 7. And I've got a little secret for you. So that is equal to lambda xx applied to 7. Those have the same meaning and scheme. So let really can be defined in terms of lambda and a procedure application. They really are the same thing, which we'll see in a minute when we get into macros. So anyway, so let is sort of like a syntactic shorthand or syntactic sugar for dealing with lambdas and applications. So sometimes we just want to have a local variable, and we don't want it sort of polluting the namespace. So here, we're saying x is bound to 6. Maybe we don't want to have x defined at the REPL at all. So starts out x isn't bound. If we use a let expression, x still isn't bound. It's the same as if we did lambda and an application. X still isn't bound, so x is local. So so we're going to combine let with a quasi-quote and an unquote to see how you might use it in practice. Yeah, it is kind of mind-blowing that let and lambda are the same. It's really, really cool. And we'll see, we'll write a macro for that in a minute. Let's take our quasi-quoted expression here and replace x with this. So here we have a let expression. We're saying that within the body of the let, x will be 7. And now we're returning as the value of the let expression this quasi-quoted list. So we should replace the value of that unquoted x with 7. And sure enough, we get 3, 7, 17. So this is an example of the sort of expression that you might build up with the quasi-quote. It may be more likely that you actually have like a lambda expression, like lambda x. So now this is more interesting because in the previous example, we knew x was 7, so we could have just substituted ourselves. But in this case, we have this procedure, anonymous function, that will take some argument that we don't know what the value of that argument is. So I can go ahead and apply that anonymous procedure to whatever value I want. So I could apply it to 8, and now I get back 3, 8, 17. So this is really the sort of use you're going to see. And maybe I even want to give this function a name. So I could say define, my list, make my list, I guess. Maybe I could call it make my list because it's really constructing a list. Do this. Okay, so I can say make my list of 9, and then I get this list 3, 9, 17. I can say make my list 10, 3, 10, 17, so forth. Okay, so that's a sort of a nice convention. I don't have to just pass in numbers. I could pass in foo, or apples, or a list, the list ABC. And that would all be placed there as well. I'll show you one more thing having to do with quasi-quote, just because you might see it. I'll make another version, make my list flatten. And instead of comma, I'm going to use something called comma at, which is unquote splicing is the technical name, unquote splicing. So this is like the same as before, except now when I pass in the list ABC, instead of getting the list ABC, the parens are removed from it. So the splicing form, basically you can think of it as removing the parentheses. Then you're splicing the list in to this other list to sort of flatten it one level. So that's another operator that you'll sometimes see with quasi-quote. It's not used as often, but it's good to know that it exists. Okay, so that's unquote splicing. And similar things kind of come up when you deal with macros and so forth. But anyway, that's quotation, quasi-quotation, unquoting, that sort of thing. Okay, so that's a useful thing to know, and it's also, I'll show you one more thing. So you can actually nest these quasi-quotes and unquotes and so forth. So I can quasi-quote the list ABC, but I could have some unquoted expression inside of that, another list, or I can make a procedure call. So I could say or. Okay. So if I have that expression, well, the thing that's quoted, the expression that comes after the unquote, we're going to evaluate that just as if we had typed that expression with the REPL, or within whatever the context of that expression is. So in this case, we evaluate that function call. We'll call it a plus. Right? So you don't just have to unquote a single variable reference or something like that. This can be an arbitrarily complicated expression. And in fact, this expression itself, we could call append of two lists, let's say we'll call foobar, append foobar to quote as or something like that. So I can call something like append. And not only that, but I can actually put a quasi-quote inside of the unquote. I can do baz, comma, car of the list BEF. So I can build up all sorts of really complex expressions where I'm nesting the quasi-quotes and the unquotes, as long as they can match up in some way. If I didn't put the unquote, then this quasi-quote and this unquote are not going to do what they would do otherwise. Basically, you'll see that the quasi-quote and the unquote end up in the final expression, right? Because we didn't unquote the call to append. So this entire part of the expression is, this entire list is actually treated as if it's going to be quoted. So because this back quote here, let's see. So we got two back quotes and one comma. Yeah. So anyway, if I remove that back quote, then that comma takes in actually gets evaluated. So anyway, the back quote and the comma turn out to be quite useful. It can be a little hard to read, I guess, if they're really deeply nested. But just like anything else, I think that's something that just you need a little experience to get used to. Just like working with cons and car and cdr, it's the sort of thing where I would just recommend you spend 20 minutes playing around with back quote and comma and comma at. And if you do that and you play around with the nested forms of them, it'll become second nature. Most of the time we use the back quote and the comma, it's going to be pretty simple, so it shouldn't be particularly difficult to read. Anyway, so that's quoting and unquoting and unquote splicing, and you can play around with all sorts of things like that. I should also just point out really quickly that just like you can quote things like 5, you can also do a quasi-quote of 5. So it doesn't even have to be a list. It could just be some other value. You can quasi-quote #f. So these values like 5 and #t and #f, these are what are called self-quoting literals or self-evaluating literals. So it doesn't matter if you put a quote in front of 5 or not. Just get back 5. Doesn't matter if you put a quote or unquote in front of #t. Just get back #t, and #t and 5 can kind of stand on their own. They don't need quotes in front of them. Okay, so that's plenty about quotation. There's a lot more we could talk about, but that's kind of enough to get started. And we're going to look at some pattern matching. We're going to use a pattern matching macro. And since we've already mentioned macros a couple times, and we looked at syntactic forms, and saw that something like cond or lambda or quote is somehow different from something like a variable bound to a procedure. Let's just talk about macros for a couple minutes. And this is, you can have a whole course in macros easily. They're very interesting topic and scheme handles macros differently than other languages. Certainly Racket has a very advanced macro system that's sort of gone beyond Scheme's macro system in some ways. So, so both Scheme macros and Racket macros are what are called hygienic. And so that adds some new challenges, but also adds some new capabilities to macros. So if you're familiar with something like C-style macros, this is going to be, in many ways, much more sophisticated. If you're familiar with macros from another Lisp, like Common Lisp or Clojure, this will be reminiscent, but details will be quite different. And if you've never seen macros at all, well, this will be hopefully eye-opening, because one of the great features of Lisp is, people say that Lisp is a programmable programming language, and it's an extensible programming language. It's a programming language where you can change the language. So that's a very interesting, very powerful approach. And when a Lisp programmer is writing a complicated program, they'll often change the language and maybe make one or more languages that are special purpose languages to help them solve the problem. And what we're going to be doing later when we look at miniKanren is, basically defining an extension to Scheme or to Racket or whatever that creates a new domain-specific language for logic programming. And we'll be using macros to do that as one of the tools. So the basic idea is that we're going to be able to change Scheme and extend it and give Scheme new syntax, which is quite powerful. It's a syntactic abstraction. So macros and syntactic abstraction. And that's really, like I said, is just going to be a very, very thin slice of the idea of macros. You could spend a career studying macro systems and working on macro systems. So let's just go back to the example we saw before. I told you that let x be 3, and I don't know, say we want to, actually I'll give you somewhat a little bit more complicated example. Let x be 3 plus 4, and we're going to return times xx. Okay, so here's a little let expression. And so how does let work? So we're going to bind this variable x to the value of the expression on the right. We evaluate this expression, so we get 3 plus 4 is 7. And now x is going to be bound within the body of the let. So x will be bound to 7, and now we're going to multiply the value of x by the value of x, which is 7 by 7. So we should get back 49. Okay. That worked. All right. And what I said was let is the same as a lambda expression immediately applied to. So in particular, we're let binding x. So x is going to be the variable for lambda. And the body of the let expression is going to be the body of the lambda expression. And then the argument that we pass into lambda is going to be what we bind x to. That expression is the same as this procedure application. I'll format it a little bit differently to see. So here's the lambda part. It's right here. And here's the argument expression that we're passing, whose value we're going to pass into the procedure we get from lambda. Okay, so that expression should also evaluate to 49. And sure enough, it does. And so the interesting thing is that these two expressions, the let and the lambda, both of which evaluate to 49, they're equivalent. These two expressions are equivalent. So which one is built in the scheme? Is it the let or the lambda? Any idea? I mean, one's defined in terms of the other, actually, at least normally. So what's the fundamental one that's built in? Is it let or lambda?
Got to be lambda.
Got to be lambda. Okay. So if I expanded the let, then I should get a lambda, right? And if I took the lambda expression, that should just be itself, right? Okay. Well, let's try it. So in Shea scheme, there's a sign called expand. So I can give it a quoted expression, and it'll tell me what it expands to. So for example, I can see what, well, let's just try it. Let's try the let expression and see what that expands into. Oh, okay, that's kind of hard to read. We got these weird looking things, a hash x, blah, blah, blah. I'm gonna say print gensim hash f. These are generated symbols. Ooh, print gensim. Ooh, uh-oh, did that change? No, I can't type, that's it. Okay, let's expand it again. So now it's a little more readable. So the let expression expanded into a let expression. Oh, that's kind of interesting. Well, we thought it would turn into the lambda. Well, let's go the other way around. Let's take this lambda and application and expand that. Oh, look at that. That turned into the let. Oh, okay. And if that surprises you a little bit, that's probably not. That's probably to be expected, because in many other scheme systems, it goes the other way. So let would turn into lambda, an application of lambda, and left lambda, which was what we call shorthand for saying a direct application of lambda. So a lambda expression immediately applied to an argument would not change. But in Shea scheme, the let is more primitive. Now, of course, there is just sort of a standalone lambda. So if I just take this lambda expression by itself, that can't expand to a let because we don't know what the argument is yet. So that's still a lambda. But if you apply a lambda expression to its argument in Shea scheme, it turns that into a let. And if you expand a let, that just stays a let. So that's a little bit different than it is in, say, Racket. If you try this in Racket, you'll see the opposite result. Let will turn into left lambda, and left lambda will stay itself. So that's very interesting to see that in scheme, of course Racket is no longer a scheme, but the idea is that different scheme implementations are allowed to decide what they want to consider the core forms. And so it's up to the implementer if they want let to be primitive, or if they want that to expand into a lambda and an application. So this, and for Shea scheme, it may be that this is an optimization, it makes the optimizations easier, whatever. For whatever reason, the developers of Shea scheme, Kent, and the other folks who worked on it decided that let should be primitive. Yeah, it was much more fun to be wrong on this one. That's right. So, this is interesting to see that it works differently. All right. So let's say we want it to do it the other way. So we could define let to turn into lambda. We could define our own special form. Let's call it my let. And so we want my let to behave similarly to let, and we want my let to turn into lambda. So let's say we didn't have let in the language at all. So we want my let to behave the same way as let works, and that should evaluate to 49. Okay, so we're going to play a little make-believe. Let's say let didn't exist in Shea scheme, and we're going to redefine, we're going to define our own version of let, and we want that to expand to lambda. So we're going to say that this not only should have the value of 49, but really what it should do is expand to this lambda expression and the immediate application of the lambda expression. And so we want my let to expand to this other expression. So that's what a macro does. You write some call to the macro, a macro call, and the macro call expands to other more primitive expressions in the language. Okay, so the idea is that once you have a macro system, then you can define more of the language or extensions to the language using the macros. Okay. All right. So we're going to define my let. And I'm going to use something called define syntax of the macro of my let. And we're going to use sort of the simpler system called syntax rules. There's another system called syntax case. There's an extension to that in Racket called syntax parse. There's also sort of lower level macro systems and so forth. But we're going to use syntax rules, which basically is going to run in all the systems. It's sort of a simpler version of the macros then. And I'm not going to get into the details of every aspect of syntax rules. If you want to know more about macros, we can do a few more examples. But I just want to show you a simple macro and allow you to kind of wrap your head a little bit around the concept of macros. And that'll be helpful when we look at miniKanren later. If we want to, we can do a little more macro stuff, but because it is very interesting. But anyway, I'll do something simpler right now. So now what we do is we write a mylet expression. And, so we had x bound to some expression e. So our identifier x bound to expression e. And we had some body for the let expression. Here's the body. So, so we have this identifier, the x, and here's our expression e. And then here is our body. Is the part below. We'll give some names to these things. I tend to use x as names of identifiers. All right. So that's what our expression looks like. Okay. So in that case, what should we expand to? So this is our pattern that I'm writing right here. And now I have to write what's called the template, which is the code that it should expand to. So what should my template be if this is my pattern? Based on what we saw here. Any ideas?
Start by just pasting the expansion.
Yeah, I was pasting this expansion. So we know we have to have a Lambda, we have to have an application. And of course, this example is a little too specific, but we can do the same thing we did before. So xx times xx, that's what we called the body, right? So I can just put in body here. And the plus 3, 4, that's what I called e. So that's it. That's my macro. Let's see if I define this macro. See what happens if I do my let. Give me 49, and we can expand it. And you can see, sure enough, it expanded to the let. Now, we expected to get back, oh, of course. Okay, so why did we get the let there? Because what happened was it expanded to lambda x times xx plus 3, 4, and then a shade scheme expanded that or turned that into the let expression. So that's why we're seeing a let instead of the lambda in the application, because we turned it into the lambda in the application, and then shade scheme turned it into the let. So that's actually kind of funny. It doesn't matter; they're equivalent, so it worked. But my let gets converted into lambda in application and then turned into a regular let. So that was kind of funny. Anyway, you might wonder what this hash 2% plus thing is. So that's a representation of shade scheme's built-in plus procedure. And here's a representation of shade scheme's built-in times procedure. So, plus is, defined to be, plus is just a variable bound to the addition expression. So I could define plus to be whatever I want. I could define plus to be 5, and now it's 5. But this built-in thing, this hash 2 blah, 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 that is always going to be bound in shade scheme to the plus addition, or plus thing. So I can call that and say plus 3, 4. So even though I define the top level variable plus to be 5, Shade's built-in internal special version of plus is the same. And so this lets Shade scheme be sure that what it thinks plus is the honest to goodness plus, and it also allows it to do optimizations as well. So when you look at these expressions, that's why you see things like that. things like +2, this #2% thing. So the other thing is, there were these print gensum, if you remember that. I said print gensum false. Let me turn it back on. So if we expand it this way, we see this kind of nastier looking expression. So we can still recognize this times, for example. But we have these identifiers, this hash x, and then this horrible looking thing here. And you notice it's actually the same down here. This is equivalent to the x and x bound to +34 and x times x. Those are just x. But these identifiers are what are called gensims, or generated symbols. So if I expand it again, we'll see that it changed. So instead of having a -1, it became -2. So that's a different identifier. And this horrible looking symbol name is actually a uniquely generated symbol. So this is to guarantee that even if there's something already defined called x in our system, we're not accidentally shadowing things or clobbering things or grabbing variable capture or things like that. So this is the hygienic part of scheme macros. Scheme macros make it so that you don't have to worry about these names. Even if there's already something called x in the system, or if the body contains some identifier that's being shadowed, things like that. These gensims are trying to protect you from getting into trouble. And to really do justice to how these gensims work, I'd have to give a couple examples. If you give examples of and or macros, you kind of see how it works, but that's maybe a little out of scope for today. But anyway, just know that if you do an expand, you'll likely see these identifiers that look kind of tricky to read. And if that's the case, you can do print gensim #f, and then it'll look a little easier. Okay. There's a whole art to writing these macros, and so I'm not going to get into it right now. But you should know that you can define new syntax in Scheme, and you can even do things like redefine Lambda in Scheme. So you can redefine Lambda to behave slightly differently, and sometimes it's actually useful. For example, maybe you want to count the number of procedure calls in your program. So you could define your Lambda to increment a counter whenever a procedure application happens, stuff like that. So you can do things like that in Scheme pretty easily. So it's quite powerful and quite flexible. In fact, you can even define entire layering of languages and stuff like that. It's very, very powerful. Anyway, so you should know that you can extend the syntax of Scheme, and this is a simple example with let. There are much more sophisticated examples than let, and you can also write recursive macros, just like you can write recursive functions. One of the recursive macros that you might want is something called a pattern matcher. And in fact, we're going to use a simple p-match. And let me just make sure I find the one. A bunch of versions of this. Yeah, I think this one's good enough. Let me just bring up my p-match real quick. The original p-match had some things in it I didn't like, so we've changed p-match a little bit. See, polyconf, I think, p-match. Yeah, okay. So I'll grab that. All right, let me cut this over to there. Okay. Here is a much more sophisticated macro that was written by Oleg Kiselyov. And I modified it, and I think Jason and Dan may have modified it additionally after this. But anyway, we're defining or Oleg defined syntactic expression or a macro called pmatch, which is a pattern matcher. And so you could see the syntax rules part. And here there's, instead of one clause, one pattern, and one template, you can see that there are two versions of it. And it's calling this auxiliary macro, which is recursive. And you can also see that instead of having the list after syntax rules be empty, he added else and guard. So those are sort of auxiliary keywords, like else and cond. Pmatch is going to have an else. And so it's going to have something called guard. So anyway, got this pattern matching thing, and it's got the auxiliary, and it's a relatively short macro, or 3 macros, and 2 of them are recursive, I believe. Is this recursive? Yeah, that's recursive. So it's not super long, but it's actually an interesting macro. This is what's called a continuation passing style macro. So if you really want to get into macros, this is actually an interesting one to look at and try to understand. But the pmatch, which I'll have to have a link to this or put it up. Pmatch is going to be useful because it's going to allow us to extend scheme to do some pattern matching. In fact, it shows some examples here of showing the grammar for pmatch. I think I remember how this one version of pmatch works. So let's go ahead and start with scheme again. So what I'm going to do is I'm going to tricks hashbang uf. If you add this to a scheme file, hashbang uf, that says it's end of file. So scheme will not try to read anything after that the special I don't know, symbol or whatever it is. So it's going to ignore everything after that point. So I am going to load pmatch. I think that was SEM. All right. And then once I load that file, I will have an extended version of scheme that knows about pmatch. So let me try loading foo. Is that SEM now? Okay. And if I type in pmatch, it says invalid syntax. So that actually means it's working correctly, because if I type in some random thing, it'll say it's not bound. So it's just saying I'm using invalid syntax for the pmatch, because pmatch is a macro, so I need to give it something that's syntactically correct. So I can just try something simple. So I could pmatch on the list ABC, and the way it works is now I can have clauses. So I can have a clause that's going to have a pattern, which is first.rest, and let's return the first, else, well, no match or something like that. We'll just say we didn't match. Let's try this expression. Let's try evaluating it. I'll explain what it does, so it works. Okay, great. So what's happening is we're matching on the value of an expression. So our expression in this case is this quoted list ABC. And now what we're doing is we're giving a pattern. This is sort of like a cond expression, except instead of having an explicit test, which might call a predicate or something like that, we're having a pattern, which is just sort of like the pattern in the syntax rules macro, actually. So what's really going on here, and this is why I wanted to show you the back quote and the comma first, is that this pattern has an implicit or invisible back quote in front of it. By the way, if you use Racket, Racket has a form called match instead of pmatch that's built into Racket. It requires you to explicitly put the back quote in its patterns. But in pmatch, you don't, in fact, don't you have to, you shouldn't, because it means something else. So, so the back quote is implicit. So we have an implicitly backquoted list here, or expression. And so the commas go before, basically identifiers that we want to pattern match or bind to the list that was coming in. So if we match against the list ABC, what's happening is we're saying, okay, we have the pattern, which is a pair, taking the car and the cutter, basically. So the car of ABC is going to be bound to first, and then the cutter, or the rest, is going to be the list BC. So this is a pattern match where we're creating as a pair. We could also have a pattern where we do something like 1, 2, 3. So now we're saying the list has to be of length exactly 3, and the first thing in the list we're going to call 1, and the second thing in the list we're going to call 2, and the third thing in the list we're going to call 3. So let me return 2. See what happens there. And sure enough, we get B, the second thing in the list. So basically, you can think of it as this list is getting matched against this list of 3 sub-expressions. And we have the identifiers here. 1 gets matched to A, 2 gets matched to B, and 3 gets matched to C. They just kind of line up. And then within the right-hand side of the match clause, these identifiers, 1, 2, and 3, are going to be bound to A, B, and C. So if I refer to 2, that's going to give me the B. In fact, I could create like a list. I could return a list. Maybe I want to reverse it, 3, 2, 1. And so now this will allow me to create a reverse list. And sure enough, we can see CBA. So the point is, once the pattern match has succeeded, I can refer to the parts that I've explicitly pattern matched against and given names, and refer to those names as if I had those parts that I matched against. And I can have as many of these tests as I want. So I could, I could have another clause that matches only against lists of length 2, let's say. So there's only a match against lists of length 2. In that case, maybe I want to return the first part. So if I try matching a list of length 3 against a pattern that only will match against a list of length 2, this will fail. And I'll skip this pattern, and I'll go to the next clause. So if I try this, I should still get the second clause's value where I reverse the list. CBA, that's right. But if I change my input to be a list of length 2, now the first pattern is going to match, and I should get back the first thing. And sure enough, I did. I got A. So in that case, the first pattern match. So I can have as many patterns as I want. I could give it a list of length 4. In this case, the pattern which matches a list of length 2 is not going to match, or a list of length 3 is not going to match. So I'm going to hit the else case. In this case, I should return no match, that symbol no match. And sure enough, I get back no match. And if I really wanted to do sort of a catch-all, I could do that first dot rest pattern again. So this is going to match against any pair. And of course, this is a pair, as we saw in the first test. This is conjugating the symbol A onto B, C, D, E. So we know that the first part's A, and the rest is the list B, C, D. So in this case, if we returned rest, let's say, we should get back the list B, C, D. No, Emacs. Emacs is crashing up, I think. All right, I have to kill Emacs, I'm afraid. Come on, Emacs, you can do it. Force quit. All right, let me start my Emacs again. Sorry about that. Screen share. All right. But again, so in this case, I've got a list of length 4 I'm pattern matching against, and my patterns are a list of length 2, a list of length 3, any pair, and then else. So let's see. It should match against the pair case, in which case we should return the rest of that list, B, C, D, sure enough. And now if I passed in, if I pattern matched against like 5, that's totally legal also. In this case, 5 is not a list and it's not a pair, so none of those first clauses should match, and instead I should get the no match at the bottom. So let's try that. No! Emacs, come on. Come on, buddy. You can do it. You can do it, Emacs. Oh, it's tragic. All right, I'll try Emacs one more time. I don't know why it's not happy. I might have to upgrade my Emacs or something. Let's do it, Emacs. You can do it. All right, one more time. Come on, Emacs. Whoops. Wasn't 1 minute ago. Yeah, I need a 32-core CPU to do the complicated actions of pattern matching. Exactly. You know, what's the adage that software gets slower faster than hardware gets faster? All right, let's try it one more time. That's all I want. All right. Yeah, I got no match. Good. All right, hopefully Emacs will be happy now. Okay, so that's a very, very brief introduction to pattern matching. You know, and remember that we have these sort of implicit backquotes on these patterns. And of course, in practice, you know, we're not going to pattern match usually against a concrete value. What we're going to have is probably a function. You know, where we're going to have like lambda x or something like that. A lambda, yeah, you know, some value like that. And then we're going to pattern match on x. So this is how you would actually do it. So maybe we're going to have, I don't know, define, you know, my match to be this function that's going to take an x and do whatever. So let's just try my match. If I do my match of 5, I get no match. If I do my match of ABC, reversed. If I do my match of ABCD, get the rest. You know, so those sorts of things. So that's a simple example of a pattern matcher using pmatch. And so pmatch, let's remember, is not actually built into Scheme. This is a syntactic extension or syntactic abstraction. So we extended the syntax of Scheme so that it now knows about pattern matching. Okay, so that's part of the power of these macros. And so this is something you can't readily do in most languages. Like if you wanted to do this in Java, you know, how would you add new syntax to Java, or how would you change how a for loop works in Java or something like that? You know, you could write some sort of preprocessor or write a compiler or something like that, but there's no simple way where just in a few lines of code you could redefine how the built-in parts of the language work. But you can do that in Scheme. And of course, with great power comes great responsibility. So you do have to be careful with working with these things, but this is one of the advantages of Scheme. The great advantages is the macros. And so Lispers love their macros, and schemers particularly love their macros. There are all sorts of kind of holy wars about whether or not common Lisp macros are the right way to do it, or whether or not Scheme hygienic macros are the right way to do it. I think the bottom line is, if you don't have a macro system at all, you just can't play these sorts of games at all, or do these sorts of abstractions. So it's better to have a macro system than not. The schemer is convinced that their approach is sort of the right way to do it. I will remain neutral on that issue. I think there's more like, I think in some ways the people in the common Lisp community are sort of talking past the people in the Lisp community or the Racket community in terms of the macros, and that the languages have significantly different design trade-offs, and so that in any case, I think the hygienic macro system is right for Scheme and right for Racket. Whether or not it should be a little bit different, that's I think up to the people who design Clojure and stuff like that. So anyway, but if you're using a Lisp, I would recommend that you learn about the macro system because it is very powerful. Okay, so now we have a pattern matcher, and we have the ability to pattern match very succinctly against certain types of patterns. And this is really cool because now we can very easily write down patterns for things like Lisp or scheme expressions. So we can do things like pattern match against a quoted scheme expression. So if you remember, so we have our old example of +3, 4. And if I run that, it values to 7. Or if I put a quote in front of it, now I get the Lisp +3, 4. And I can do the same thing with like Lambda XX. So this is the identity function. It creates the identity, so it's a Lambda expression that evaluates the identity procedure. Now if I put a quote in front of it, now I get back the quoted expression. And if I call a val on the quoted value, now I get back the procedure, just like if I call a val on the quoted +3, 4, I get back 7. So I can quote some piece of code, and I can eval the quoted code to get the value of it. And so we're going to end up writing our own eval, and it's going to work on quoted expressions. So once you have a quoted expression, +3, 4 or Lambda XX, now you want to be able to manipulate the expression if you're writing something like eval. And so to look at the expression type and tear it apart, it's very handy to have a pattern matcher. So now we can do things like pattern match on Lambda expressions. So we could write, we can define something like parse, and that can take an expression, Lambda expression, and I can pattern match on the expression. And now I can decide what types of expressions I want to pattern match against. So one pattern could be a Lambda expression, Lambda X body. So maybe a Lambda expression looks like that. And if that's the case, maybe I say that's true. And else I say it's false. So here's a little parser that's going to tell us, it's actually more like a validator. It's like, maybe I should call it like valid expression. So this is going to tell us if we have a valid expression. So we have to decide, what sort of expressions we want to handle. But if I call valid expression on a Lambda expression, like Lambda y times yy. Oh, I forgot. It has a question mark. Valid expression, and it gives me true. And if I give it something else that we haven't told it about, like 5, it's going to say, no, that's not a valid expression. So at this point, we can start adding other expressions to our language. So we might add, for example, numbers. So I haven't shown you how to use the pattern matcher to pattern match against something like a number. I believe the syntax is something like this. Let's see if I remember. So I have some expression. So I'm giving basically an identifier n, or a variable n. So the comma in syntax actually will match against anything. I'll match against any expression. And then I can have a guard that checks against the value bound to n, that expression coming in, to see if that expression is a number. And if so, the guard says, OK, continue. Otherwise, the guard fails, and we go on to the next clause. So basically, you can think of the guard as being part of the pattern. So not only do we have to match the pattern, but the guard also has to return true. The predicate in the guard has to return true for us to go on. Otherwise, it's considered to be a failed pattern. I believe that's how this version of PMatch works, so let's try it. So let's see if 5 is a valid expression now, and sure enough, it is. So we can give it some complicated number, and now we can handle numbers. Okay, great. What about booleans? Oh, a boolean is not a valid expression. So we can go back in, and we can add another clause for booleans. So we can say, okay, if we have B, and B is a boolean, then sure enough, that's a valid expression. So I'll add that. Now we try boolean, and sure enough, that worked. And if I try boolean of false, that worked as well. So I can start building up expression by expression anything I want to handle in language. And so I could do variables as well. So I could say, or symbols. I could do symbols. So say I have a symbol, X, symbol question mark of X, then that's also legal now. So if I ask if quote X is valid, yes, that's allowed now. Or quote foo, I can do quote foo. Valid expression. I can build these up a little bit at a time, and I might even do procedure application. So what does a procedure application look like? Well, we have some expression E1 applied to some expression E2. So E1 had better evaluate to a procedure, and E2 is going to be the argument or whatever. But that's going to be, let's say we only allow procedure applications with one argument, just like we're only allowing lambdas with one variable, then that's fine. We'll say that's legal as well. So this is the procedure application case. Application case. So this is what we're going to do when we're writing various types of programs that manipulate other scheme programs. Is we'll write things like this program that looks at different types of expressions and manipulates them. So if I wanted to do lambda x applied to 5, so that is a valid expression. If I did lambda xy applied to 5, 6, that's invalid because my lambda is taking too many arguments, and I'm getting too many arguments in my application. So if I check my lambda with 2 arguments, that doesn't match because we're only matching lambdas of 1 argument. And so we can start seeing the types of expressions that we're deciding to handle. I could handle expressions with more than 1 argument if I wanted to. So for example, I could do something like x star and put a guard. And I could put a guard saying, that x star is a list, or I could define my own list of symbols or something like that, that kind of thing. And so that way I could check that sure enough, x actually has to be a list of symbols for that to work, if I wanted to handle any number of arguments, stuff like that. But right now we'll just restrict it to handling a single x. So these are the sorts of programs that we're going to write, and having a pattern matcher and having the ability to do these kind of quasi-quoted expressions is really handy. I should also point out, I didn't say explicitly, that if we put in the implicit quasi-quotes and just think about what these patterns mean, I think it's pretty obvious what this list means because we know about quote and unquote. But this may be a little less obvious. So here we're back quoting, or so here we have quasi-quote and unquote. Here we have quasi-quote of unquote of x. So quasi-quote and unquote basically destroy each other. If you have a quasi-quote immediately followed by an unquote, that's the same as just writing the expression after the unquote. So that's just the same as writing x itself without any quotation. So that's, because it's implicitly quoted, that's why we have to write the comma. It might look a little strange, but if you write lots of these patterns, you get used to it. It becomes second nature. Okay, so that's the sort of thing that we write. And in fact, we can write one of these valid expression things for what's called the lambda calculus. So let's remember if we talked about this, but the core of scheme and of many other functional languages is based on something called the lambda calculus, which was created by Alonzo Church. And for the lambda calculus, I'll put it down here. Actually, I'll put it up here. Lambda calculus has three basic types of expressions. So like x, which is basically as a variable, and it also has lambda, lambda x, and then here's some other expression. So this is called lambda or abstraction. Lambda calculus is called abstraction. And then you have application, like E1 applied to E2, so E applied to E. So two expressions applied to each other. So that's application. Now, the way you would actually write this, like in a book on lambda calculus, syntactically would be somewhat different. You wouldn't have quite as many parentheses, but this is basically a one-to-one correspondence. Lambda calculus also has a couple other differences to scheme. In addition to the syntax, lambda calculus, so scheme is what's called a call by value language, which we'll get into more when we look at interpreters and stuff like that. Lambda calculus is not. Lambda calculus has some laziness in it, and there's some other issues. But anyway, the basic idea is that scheme is an extended call by value lambda calculus. So true lambda calculus, the simplest version, all the lambdas can only take one argument. All the applications only take one argument coming in. And this is it. You have variables, lambda or abstraction, and application. And it turns out that you can implement any function that's pure in the lambda calculus. So any sort of computable function can be implemented in lambda calculus. It's Turing complete. You can encode the equivalent of a Turing machine, all that sort of thing. So any sort of mathematical calculation that's decidable, you can express in lambda calculus. So only these three little expressions, three types of expressions, but it's enormously powerful. Sort of the heart of all computation is encoded in these three operators. So anything else in scheme is really extra. It's not technically needed. You can encode arithmetic, you can encode numbers using the lambdas and all this thing. There's what are called church encodings of numbers. Very interesting stuff. If you're interested in that, I refer you to Matt Might's blog post on church encodings of numbers. Arithmetic. You can actually do, addition and subtraction, all sorts of things. Basically, any operator you want. You can do conditionals. You can express things like if using lambdas. Very, very clever. But it turns out that even though you can do that, it's not very convenient. So this is what Alan Perlis referred to when he said, beware the Turing tar pit, where anything is possible, but nothing of interest is easy. So that just straight lambda calculus is a Turing tar pit. You want to express any interesting computation, it gets very difficult to deal with and read, and very slow and so forth. So, in practice, if you're using a functional language like Scheme or Racket or Haskell or ML or Scala or Clojure or whatever, you want some extensions to lambda calculus, and you also might change it to say be call by value. But anyway, this is really the heart of Scheme, call by value lambda calculus. So whenever we're dealing with, say, an interpreter or a type inferencer or something like that, the rules that you really have to be paying attention to are the rules for the lambda calculus. Because if we can do lambda calculus, then in some sense that's the core part, that's the hard part. Anything else is kind of syntactic sugar in a sense, or just something to make our lives easier. So you'll see these three lines come up over and over again when you're looking at interpreters or other artifacts like that for functional languages. Okay, so this is so important that let's just go ahead and write our pattern matcher here. So we had this valid expression thing. So let's do a similar thing. So let's say lambda calculus expression. Okay, so what do we need? Well, we need the ability to express variables, and we'll represent our variables as symbols. So we already have the x case, so we have that. We don't need booleans, not needed, not part of our lambda calculus. We don't need numbers. We can encode those as lambdas. We do need lambda, and we need application. Okay, so you could see that all we had to do was remove some of the cases already. However, we do need to be a little careful here, because something we didn't really do in our previous example was have a recursion. So when we were checking the expression type, this was only at the top level. For it to work properly, it doesn't just have to be a lambda at the top level with any arbitrary body. It doesn't just have to be something that looks like a procedure application at the very top level. We also have to go and make sure that the body is a legal lambda expression. We have to make sure that E1 and E2, those expressions are legal lambda expressions. So what we have to do is recur. So here we're going to recur on the body. Down here, we're going to recur, make sure that E1 is a valid lambda calculus expression, and make sure that E2 is a valid lambda calculus expression. And what we're going to do is combine those values with an AND. So they both have to be true. So AND is going to return true only if and only if, the recursion on E1 returns true and the recursion on E2 returns true, or return the non-false value. Okay, so we have to recur on both and then combine those, or check out both. And here we have to recur on the body. And what we might want to do if we really are trying to be, yes, the question is, what do we do on X? So X is a symbol, so should we recur on X? Does that make sense? So we have two X's here, right? One is the variable case. This is the variable case. This is the lambda or abstraction case. And then here's the application case. I won't call it procedure application anymore. This application. Okay. So we have this X here, and we have this X here. Okay. We're just trying to see if these are syntactically valid. So we don't actually have to recur on them. What we do have to say is we need, if we really want to be stickler about it, X should be a symbol, right? X shouldn't be, a list of numbers or something like that. So what we should really do is add a guard, and we should add a check to see, not number, symbol. Is X a symbol? And remember that the guard is really part of the pattern. So syntactically, we have to have a lambda, we have to have a list of one symbol, and then we have to have a body, and the body itself, we're going to recur on to make sure that that's a valid lambda calculus expression. With the application case, we're going to have a list of two expressions to represent our application, and we're going to recur on both of those sub-expressions, and they both had better be expressions. So our two base cases are going to be when we have a variable. I'll just try to make the notation consistent. If we have a variable, a symbol representing a variable, that's true. And if we have a lambda with a valid body, well, this isn't really a base case because we have to recur. So really the only base case, in some sense, is eventually we're going to have to hit variables for our leaves here. Okay. All right. So let's see if we can run this thing and give it some expressions and make sure this actually seems to work. So let's see. How about y? That should be a variable, a symbol representing a variable. Okay, sure enough. Or we can give it some big name. That works. What if we give it 5? Nope, that is not a lambda calculus expression. All right. What if we give it lambda zz? That is true. What about lambda z5? That is false. So we can see that we're recurring in the body. We can have a nested lambda. That works. We can have an application. We can have that lambda applied to itself. And that's true as well. Okay, so we're handling our lambda calculus expressions now. We can check to see if those are syntactically valid. So we're using a pattern matcher, which is a syntactic extension of scheme. We have these implicitly quasi-quoted patterns, and then we're making sure when appropriate to recur on the sub-expressions. And furthermore, we have these guards to try to make sure that when we're maybe matching on a little more than we'd want, we're checking to make sure that the variable is, in this case, of the right type, that it's a symbol. Because this comma x will actually match against anything. It'll match against lists or whatever. Same with this comma x. That will match anything. It'll match a number or whatever. So we need to have this guard to protect against getting the wrong values. And the guard, remember, is considered part of the pattern. So both the pattern has to match and the guard has to match. And furthermore, when the pattern matches, we're binding x and body as identifiers. Those will be bound within both the guard expression and the body of the right-hand side, if you will, of the p-match clause. And we'll be able to refer to those, okay? So that's an awful lot, actually. This lambda calculus expression program might look simple in some ways, but we've introduced an awful lot of ideas. Macros, pattern matching, quasi-quote, unquote, guards, so forth. Lambda calculus. So, any questions so far? That's a lot. In fact, that's enough that it's probably like a good place to stop. And then next time we can talk about variables, lexical scope, shadowing of variables, free and bound variables, environments, and start writing programs sort of like our syntactic checker that will actually do things like look at the environments of an expression or find which variables are free and bound or whatever. We can start working towards our interpreter next time. Any questions? I'm probably going to stop the broadcast after these questions, and we can just talk if we want to hang out for a few minutes. Okay, well, I will post this code, and I'll post the pmatch code and link to them in the video, or in the YouTube channel. So next time we'll pick up and we'll do things having to do with variables and lexical scope, and write some more interpreter parser type things. Okay. All right. Till next time. See you then.